1 like and I haven't even done anything yet. Gee. They like me. They really like me. You can't hear me. Okay. Well, I've got the thing turned up, so I can hear me. And normally, if I can hear me, you can hear me. So I would check your volume setting. That might be the first place to check. And, like, I've got audio coming in. Thank you, Ivan. Okay, good morning! Hello, everyone. Yes, cool. Well, looks like our, that's the thing about viewing numbers, is like, as soon as people sort of get the idea, oh, it's not the end of the world if I don't catch the lecture, then attendance just goes comp sci and coffee on a Monday morning. Yes, indeed. Personally, actually, I am having the last little bits of oolong tea, which were in the jar. So, you know, green tea in the morning, black tea in the afternoon, coffee with breakfast, and herbal tea at night. Yeah. Coolio. All right, so, yeah, so there's not much going on in the way of announcements. There was a correction posted to one of the assignment test cases over the weekend. It looked like one of the hidden test cases was not made hidden. So, essentially, the solution and fix to that is don't worry about it. Just don't worry about it. It was not meant for human eyes. I agree. Oolong is the goat. Jasmine is like a close second, but oolong, that's the good stuff. Although, I'm now out of the oolong, so I'm going to have to be drinking all of the other types of tea that nobody drinks because nobody likes them particularly. You know how you just kind of accumulate tea? Well, I have decided that my 33rd year on this planet, it's time to drink all of the tea that has been accumulating in the cupboard for the previous, 30 years. It's not quite that bad. I wasn't collecting much tea when I was 8 years old. That was sort of before the loose leaf tea craze, but anyway. Anyway, let's get into some computer science. Computer science is the best subject. I am sure everybody likes this class more than all of their other classes. So let's talk about computers and junk. So we left off with this idea. We were talking about how to design large programs, and an essential component of designing large programs. Generally speaking, when we're talking about designing large programs, the larger the program is, the higher the likelihood is that it won't be just you working on it. So, in general, there's good practice and there's bad practice. Good practice is leaving notes for people to give them some idea of how your functions are to be used. Bad practice is not doing that. Bad practice is assuming that the user of your code will sort of spontaneously and intuitively know what you were meaning by some function or another, sort of without any notes or documentation or aid of any kind from you, or even worse, that they will read your code to understand what's going on inside of your code. This is not a good place to be in. So, we document functions. In Python, we have this particular thing called a doc string. Let me just... Again, this is the reason we're so far behind. Documents, McMaster Teaching, 1MD3, the current semester, code, get it, topic. Do I have a topic 5 going? No, I don't yet, but that's okay. We'll just apply a doc string to one of the things in topic 4. So, like the make change algorithm. So, when you are applying a doc string to a function, you can put it down here, include three quotes on one side, 3 quotes on the other. This denotes it as being a doc string. In Python, this is also the only way to do multi-line comments for those of you who are used to other languages. So one of the very interesting and useful things about a doc string is that it's a way for you, the user, to be able to apply help text to a function. So, def make change. This function takes a tuple of coin denominations and a target value, and returns the number of each coin you need to make change. Save that up. Correct the spelling mistake. There we go. So, the interesting thing about a doc string is once it's been put in, if you call the help function on the function that has the doc string, this string explicitly is what's going to be shown. So if I Python 3 this guy, I think I can just load. I forget how you load stuff. Load topic 4.py. I'm just spitballing here. No. Okay. At any rate, if you use the help function on something like print, this text right here is given in the same manner that it's encoded in the same manner on the print function as we've encoded this string on the make change function. So that's a good way to do documentation. Generally speaking, when you provide documentation, good systems are one where the user always knows where to look for your documentation, and they don't necessarily have to open up your source code file. Generally speaking, if the user has to open up your source code to get at your documentation, then they're probably using, not a great system. So this is a way of integrating your documentation with the existing system for looking up documentation in Python, which is cool. Yes, the idea of docstring is essentially that you are creating your own documentation for your code. That's funny. Yes. So yeah, when documenting your code, there are a few things that it is usual and typical for you to include, things that are very useful. Number 1, assumptions and requirements and preconditions. Those are sort of all roughly in one category. So if, for example, you did your make change function in the same way that it was specified in the slides to, which assumes that the coins are already in order in the tuple, that's something that needs to be documented. How is a user, a random user, going to know that your coin tuple needs to be in order for the function to work properly? They're not. If they don't know that just from looking at the name, then that should go in the documentation, right? Make sense? Basically, and actually these are, oh, cool. Get out of there, you. These are good, rules for communicating in general, like even with, flesh computers, by which I mean people. So, if you're communicating with a person, it is always good to start off that series of communications with the assumption that the other human cannot read your mind, right? They cannot look inside of your thoughts and see what you mean. You must express yourself clearly and succinctly, right? You must say what needs to be said. And what needs to be said is the stuff that's going on in your brain. So, assumptions, requirements, preconditions. Yes, anything a user must know in order to use your function properly. Also, guarantees / postconditions. What conditions will the output satisfy? So long as the assumptions were satisfied. So, in computing, we have this phrase, which is our favorite phrase, called garbage in, garbage out. And this is a short way of saying, if you did not follow the, assumed preconditions for a function or an algorithm, if your input was garbage, your output will be garbage too. If you did not follow the preconditions, you will not get the desired postconditions. So yes. Cool. Here's an example of the slides documenting it. Assumes target is an int and that coins is a sequence of ints in decreasing order. Returns a dictionary with a key for each entry in coins with a corresponding int for the number of coins in that denominator. Notice that the data types of the inputs and the outputs are specified. Notice that the data structures involved are specified. Very, very important thing. If your function assumes that the user is giving you an integer, you should say that. Yes. And when you call it, when you call help on making change, you get the following spit back out at you. So far, so good. All right, so we're going to talk about recursion now. I'm going to give you guys a moment. If you have any questions about those topics, we shall answer. Bop, 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 bop. Cool. All right. So, now to talk about the meat. This is the meat and potatoes. This is the recursion of functions and recursion. We are going to talk about recursion. Recursion is a very important concept in computing. Recursion, roughly defined, a recursive algorithm is any algorithm that invokes itself at some point. So, yeah, it's like, well, we'll see anyway. So, well, I wanna come up with a good. It's almost like fractals, right? So, some of you may know this. A tree, when a tree grows, it does so in a fractal manner, and that's what that means is that if you take a look at a tree, like a an oak tree or something, generally speaking, if you examine the tree as in its entirety, it'll have a certain shape. Like the branches are so far apart, they're spaced relatively evenly. It depends on how orderly the tree is, I suppose. If you examine a branch of that tree, it will follow the same patterns of branch distances. Like it is fractal, right? recursive algorithms are similar. They are similar to that. You can think of the solution of the problem how to grow for a tree that is being solved using a recursive algorithm. Because what it essentially does is whenever it needs to grow, a structure, an above-the-ground structure, what it does is it applies the same algorithm, but on a smaller scale. This is what recursive algorithms do. And we're going to see how this works with our favorite factorial example. So in the factorial, one way of defining the factorial is you've got a base case. So if you're trying to take the factorial of 1, we just define that, if we try to take the factorial of 0, we just define that as 1. It is just 1. That's it. You need think no further about it. In theory, you could define every single possible number that you could compute a factorial for. You could define what number it is. This would essentially be the lookup table approach to the problem. However, we want something a little more mathematically interesting. So, for the factorial, for any number greater than 0, how we define that is that number multiplied by that number minus 1 factorial. That's cool. So if you remember the sort of standard mathematical definition of factorial, it is every number up to the number you're taking the factorial of multiplied together. So factorial of 4 is 4 times 3 times 2 times 1. And it has this interesting property where the one exception you make to that is 0. So when you're taking the factorial of 0, that's sort of defined as 1, because obviously if you multiplied everything by 0, the result would always be 0. But yeah, so in terms of structures of definitions, we call this an inductive definition. Induction. We're not talking about inductive stoves, although it's kind of like that. In terms of like the meanings of words, it's not like a million miles away from the idea of an inductive stove. So the idea with a magnetic induction, right, is that you have a magnetic field which appears to induce spontaneously in metal objects inside of that magnetic field a electrical current, right? It induces a current. It brings into being a current. In the same way, an inductive definition from simple principles brings into existence some mathematical object, right? In this case, a factorial. So using only these two cases, we can define every single factorial number that exists so long as it's above 0, which is fortunate because I don't believe that that's the entire domain of the factorial function as such. So when we define an inductive definition, we require two things. We require the base case, and we require an inductive case, or an iterative case. This is also known as the recursion. So the reason that this is a recursive definition is because this guy is this guy, right? But with n minus 1. We are using the definition of factorial within the definition of factorial in order to define it. Now, normally, if you were to do this in like spoken language, you would be using what is known as circular reasoning or circular argumentation, right? Generally speaking, it's like there's this this nice example. It's like circular reasoning. It's the student and the karate master. The karate master says, you must always do what this book says, and the book says you must always do what the karate master says, right? Circular reasoning. It's like, what is a fish? A fish is a fish. It doesn't make any... It makes sense, but it doesn't get you anywhere. However, so the difference here, the reason that this isn't circular argumentation is because this term will eventually become this term. That breaks the cycle, right? So some programming languages, such as Haskell, and if you're one of the comp sci guys, or if you're a person who's looking to do a minor in computer science or something like that, you're probably going to run into a computer science, a computer language called Haskell. In Haskell, everything is done recursively instead of being done with loops. So you can set up repetitive behavior with recursion in the same way that you can do so with a loop. And it's exactly this. So anyway, you can also think of it in algebraic terms as like subsequent expansion of the definition, right? You know, it's like, I'm just gonna do something down here. It's like, what is 5 factorial? Well, it's 5 times 4 factorial. What is 4 factorial? It's 4 times 3 factorial. What is 3 factorial? It's 3 times 2 factorial. Except each time you calculate that, it's a function call. That's basically recursion. Perhaps I'm belaboring the point at this point. But, actually, let's open up topic 5. Open up topic 5.py. There we go. And define factorial. Let's do a recursive definition of factorial. So, return n times n factorial of n minus 1. So that's the recursive step because it includes the call to factorial. But of course, if we actually did this, yeah, okay, let's actually do this and see what we get. Print n. So, factorial of 5. Python 3, topic 5.py. Aha! So you notice that if you just include the recursive step, the thing is supposed to stop when it hits 0, but it doesn't. It just keeps going. The base case is the limiting element. Without the base case, the thing just goes on forever. So let's add the base case. If n is equal to 0, just put the print statement up here, then return 1. Else, or if n is greater than 0, return this. So the trick is, of course, that this guy is going to cause, in order to execute this return function, this function call has to be resolved, right? In order to be able to calculate a real concrete value to return from this function, right? So execution of any call to factorial is going to need to wait for the function call which it invokes to terminate before it can come up with an answer. And the only way this guy terminates is if n at some point reaches 0. So there we go. Oh, and it should probably print the result. There we go. Ha! Well, that didn't do as much as I would have hoped. Anyway, So, yeah, 120 is the correct answer. So, yeah. So let me see if we've got any questions. Math. Philosophy, X, Comp, Sci. Yes. 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 Inception. Yes! Contemporary movie reference. Yes, 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 yes. So this is Codeception. This is Functionception. Yeah, in the same way that they went into a dream within a dream within a dream in that movie to, mind control what's-his-face. In the same way, we are going deeper and deeper and deeper in order to eventually hit the concrete layer where we return some sort of concrete solid value. That gets returned back up through a chain of return statements, and then eventually it sort of breaches the top level and you get your result. Yeah, so yeah, this is... Yeah. Yeah. However, in that movie, they only went like 3 dreams deep, in theory. So in this one, we're already going 6 functions deep, so we're better than Inception. Is recursion kind of like a loop? Recursion is kind of like a loop, yes. Yes, it is. It's very much like a loop. Actually, it kind of operates slightly differently. So if you want to get into like the real math, looping behavior is derived from Alan Turing's Turing machine. Alan Turing is generally considered the grandfather of computing as we know it. However, his was not the only model of computation that was developed around that time period. You also had the concept of lambda calculus, which was developed by a chill dude called Alonzo Church. And that lambda calculus, essentially, it's based on a system of function argument abstraction and replacement, and therefore is much more similar to conventional mathematics than the Turing machine. And the manner in which lambda calculus implements this type of looping behavior is by using recursion rather than loops. But yeah. Is there anything you can do with recursion that you can't do with a loop? Oh, no. So, here's another sort of advanced computer science bit for you. So, in computer science, we have a concept called Turing completeness. Any system of calculation is either Turing complete or not Turing complete. For it to be Turing complete, that means that the system of calculation must be capable of implementing everything that a Turing machine can do, right? And it turns out that of the 8 or so different models of computation that have been developed over the years, myself, I really only, like, Turing machines, obviously, lambda calculus I know pretty well, reasonably well. Well, not super well, but, and I've heard of Markov chains, but I've never actually used them. And I think what are they called? Automata. Finite state automata. That's another model of computation. All models of computation so far have been demonstrated to be equivalent in some manner to a Turing machine. So, because recursion and lambda calculus is Turing equivalent, you can't actually express anything in lambda calculus that it's not possible to express using a Turing machine. So that's not the question, though. Because, to some degree, if everything is equivalent to a Turing machine, why don't we just learn one imperative language and call it a day? Why do we have this, multiplicity of programming languages which are available for us to learn? What's the purpose? And the answer is, it's easier to do some questions in certain types of environments than it is in others, right? Mathematical environments. So there are questions which lend themselves to recursive solutions, and there are questions that lend themselves to iterative loop solutions. Again, being an effective programmer is very much like being an effective plumber. You have to know which wrench is the correct wrench to use on the pipe you're working on at that particular time. So, again, I always try to emphasize this kind of what's it called? Not proactive, but it starts with a P. Not positivist. Oh. Pragmatic! Yes. Pragmatism. You should view programming languages as pragmatic entities. That is to say, they are only so good insofar as they are useful. And you should look at all programming constructs within programming languages in the same manner. It's like a for loop is only so good as it is usefully applied to the problem you're currently working on, right? A while loop is only so good as it is practically applied to the particular problem you are working on. If you're, you can use while loops, but sometimes for loops are more efficient and less vulnerable to error. A lot of the time when you're working on data structures. Sometimes the structure of the program itself lends itself naturally to a recursive solution. It turns out that once you get into some of the advanced algorithm stuff, a lot of the stuff inside of that area, once you start working on trees and heaps, once you start working with graphs and graph theory, even matroids, you remember last time in class we were talking about how the make-change problem can be expressed as a matroid. Matroids are naturally recursive, right? Because you have a problem, you make one decision about it, and then you have the same problem but slightly smaller. That means that you can use the same function to solve it, right? This solution to the factorial problem is, in some sense, a matroid. Because you make a decision, and you have the same problem, but it's slightly smaller. And then you make it smaller and smaller and smaller and smaller and smaller until it resolves itself into a single answer, and then you smush everything together, and you have your solution. Yes. So, again, Haskell doesn't use loops at all. Haskell just uses recursion, and it manages fine. But, again, there are some things which are easier in Haskell and some things which are harder in Haskell. So it's up to you, the individual that has an interest in the pragmatic application of programming languages, to find the correct constructs within languages and even to find the correct languages for the particular problem you want to solve. This is kind of this is what separates the people who think they're programmers from the people who are actually programmers. But yeah, anywho, try to get through more than 4 slides today. So, this is the slide's solution to factorial, which is the same as mine, except they've written out factorial instead of used an abbreviation. Notice how we are using an if statement to differentiate the base case from the iterative case, or the recursive case. This is a good structure if you're a little shaky on the idea of generalized recursion. This is a good way of... this is an excellent way of thinking about recursion in terms of base case and iterative case. So, good. This is just printing stuff out, which, we did. Every time we recurse, the interpreter creates new scope and new variables in the function. So you're not going to have a conflict between the various variables that you're using in each call to the function. Remember how I said earlier that when referring to a variable, they always the programming language will always refer to the most local instance of that variable. This is where that gets applied, right? So when you're iterating through all of these calls to factorial, in any particular instance, you're always referring to, for example, the n parameter that is most local in the context you're working. So, recursion is a natural technique for solving problems with an inductive structure, but depending on the structure of the problem, recursion can be inefficient. In particular, in Python, if you notice, up here, we hit a problem. We hit case 991, and then we got an error, recursion error, maximum recursion depth exceeded while calling a Python object. So, some languages deal with this better than others, but generally speaking, your computer has a limited capacity for invoking function calls, right? This is what's called the size of the call stack, right? Call stack, as in the function call stack, which is the same stack as is referred to by Stack Overflow, which is the the website that probably a bunch of you have used to look up help for the assignments and such. So, computer memory is finite. Starting up a new function costs memory, so there's only so far you can do it. Whereas, so recursion is slightly more memory intensive than a looping structure, right? Which is just modifying a few variables. That being said, programming languages like Haskell, which rely exclusively on recursion, they find ways of going around these types of issues, mostly, I think, probably by simulating a call stack outside of the system call stack. But yeah, so you can hit limits on recursion. So it's not, again, there's no such thing as a universal wrench. Although an adjustable spanner is pretty close. So, so let's consider a different example. Let's consider the Fibonacci sequence. So we know that the Fibonacci sequence is defined as each number in the Fibonacci sequence is the previous two added together, right? So let's implement the Fibonacci sequence. Def fib, not big, fib. That was a funny. All right. So base case, if n is equal to 0 or n is equal to 1. We need two base cases in this case, in this particular instance, for reasons we shall explore. Then return 1. Else return fib n minus 1 plus fib n minus 2. There we go. So let's print n. Right? Cool. And print fib of 5 or 7. Why not 7? Let's do 7. Oh, syntax error. Cool. So our eventual result is 21. And this is all of the numbers that it has to calculate. So first we hit 7. 7 needs 6 and 5. 7 needs 6, 6 needs 5, 5 needs 4, 4 needs 3, 3 needs 2, 2 needs 1, 1 needs 0. Well, it doesn't actually. 2 is composed of 1 and 0, so those are both calculated in sequence. So, because we have two calls to Fibonacci here, we have effectively a branching algorithm, right? You can think of each of the call chains that are required to calculate the Fibonacci number as traveling down separate paths in a tree. Even though, in practical terms, inside of the computer, each one is done in sequence, because, you know, in a computer, computers only do one thing at a time, right? So the other thing that we can do, rather than print out the number of, rather than print out the actual number, we can keep a global counter to keep track of the number of recursive calls, right? Rather than seeing the numbers specifically, that might be more useful. So, cool. So, our value is 21, and it takes 41 recursive calls to get there, right? What if we do 8? The Fibonacci number is 34, but we need 67 recursive calls, right? Think of it like a branching tree, right? The bigger the tree is, the more branch ends it has. And this is exactly what we're seeing. Notice that there is a nonlinear relation between the number we're putting in here and the number of recursive calls that we're getting. And it's actually, it's easy. So at 20, we're at 21,000, right? At 21, we're at 35,000, right? So it's like there's a multiplicative factor. It's around doubling. It's slightly less than doubling, but it's around that. So, this is bad. Generally speaking, this makes this a bad algorithm, because if you hit like 41, see how long that's taking? Who even knows how long it can take to terminate a calculation like that? Even at 36. It's like literally right now, the computer is just crunching numbers. It's just crunching numbers. That's why it's not doing anything. So let's see if we can find something that executes in a reasonable amount of time. Yeah, so you see how long that takes to execute? About like half a second. One more. About a second. One more. About 2, you know? It's become noticeable. You get a noticeable delay each time you increase the number here. And that's because it's trying to process, like this thing is processing in that amount of time 4 million operations, you know? It's a lot. And so this is what we would call an unsophisticated algorithm. This is an inefficient algorithm because you can't call anything above 32 without it doing this. Right? Let me see if we have any comments. Cool. So, I'm just going to skip that quiz. So this is what I'm talking about when I'm talking about the branching structure, right? So if we just keep it to fib4, right? That fib4 needs fib3 and fib2. Fib2 needs 1 and 0, so there we go. 1, 0, both base cases, up you go to 2, then it, you know, contributes upwards. Notice that fib3 requires fib2. This structure is repeated. If we want to make the algorithm more efficient, one of the ways that we can do that is we can eliminate redundancy within the call structure. So how do you eliminate redundancy within the call structure? You keep track of intermediate results. The reason that we have to calculate this twice is because we're not keeping track of what the results of this are when we, if we organized our algorithm such that when we hit the second instance of a call to fib2, rather than calculate it in this manner, we can just look it up in a dictionary or something like one. Then we can get our algorithm to run much more efficiently. So this slide just demonstrates that there's a nonlinear relationship between the number n and the number of recursive calls. A purely recursive solution to computing the Fibonacci sequence is inefficient because it has to recompute the same value many times. A more advanced technique called dynamic programming remembers intermediate solutions to save on recursion. So, and just a quick note on infinite recursion. Just like it's possible to write an infinite loop, it's totally possible to write an infinite recursion. I already demonstrated this with factorial, but essentially, if you eliminated one of these cases, right, then one of these if statements, one of these branches of recursive calls would glide right past its hypothetical stopping point, right? Fib1 would require fib0 and fib-1. Once you've hit -1, you know, it's all downhill from there. You'll just continue on to infinity. An easy and tricky way of being able to not have that happen at all is to say for n less than or equal to 0, or less than or equal to whatever the base case is. Because then it'll just stop, and if it does happen to go over, then it doesn't matter, because it will be caught anyways. But yeah, you want to be careful because infinite recursion totally does happen. However, infinite recursion in Python isn't as big a problem as an infinite loop, because at least it will eventually hit its recursion limit and then stop on its own, whereas with an infinite loop, it will never do that. Coolio. So, yep. So, alright. It seems we're going to we have a few more slides to get to, so let's get through these, and then perhaps we shall, we'll probably have to do the memoized Fibonacci next time. So, when you're measuring efficiency, there are a couple of different ways in which you can measure efficiency. Number one is runtime complexity. That is to say, what is the approximate number of basic operations the algorithm will perform for a certain set of inputs? That is, how long does it run based on the input? With this guy, how long does it run based on this value? You can imagine we can chart that, right? We have this would be the x values, and the amount of time it takes would be the y values. In fact, in Linux, we have a time function that actually will tell us how long it takes something to run in definite terms, right? So that takes 1.6 seconds. If we were to increase that to 3, that takes just about 3 seconds. You see? So you can collect these data points, you can graph them, that can give you some sort of estimate. You can do math. You can math these things, right? So that's a practical manner of measuring efficiency, right? So when you perform empirical observations, timing the algorithm is a manner of that's an empirical observation, right? You're letting it do its thing and then measuring it, kind of similar to how you do a physics lab. Theoretical means looking at the thing and using your galaxy brain to determine how many recursive calls you're making for each recursive step. Like, it's not rocket surgery to figure out that this guy is going to blow up in complexity, because every time this guy is called, when it's not a base case, it's generating 2 additional calls to itself. So that's just going to blow up, you know. At the nth step, you're going to have 2 to the n function calls. That increases exponentially. That's, you know, regardless as to whether that's good or bad, it's possible to get there from a simple theoretical analysis of the algorithm itself. The other thing that you can see is memory complexity. So for this guy, although its number of function calls are blowing up, we're not declaring a bunch of memory in each of these function calls, right? So the amount of memory that's going to be consumed by it is basically limited to that which is required to invoke another function call and whatever it needs to hold n, right? So, you know, you can estimate how much memory your algorithm is taking up by looking at it as well. But that's also a thing that can be measured in practical terms. Certainly, you know, using I think it's dist something. Nope. There's anyway. You know how to get to you know, Control-Shift-Escape on Windows, and you can view all of the memory that all of your processes are using. That's a way of actually practically measuring the efficiency of your algorithm. Good. So, here are some practical runtimes for recursive Fibonacci. So you can see by the time we hit 40, we're starting to talk about, you know, runtimes upwards of 1.5 minutes, which is a lot. This is what the graph looks like. You can see runtime scales exponentially with n, very efficient for a large n factorial. So, diamond hands to the moon. So yeah, it's generally speaking, you don't want this. It's bad enough when an algorithm does this based on the size of a list, right? If the list has 100 million things in it, you can think, okay, well, at least there's some justification for processing 100 million data points. This isn't even processing 100 million data points. This is based on the size of an integer, which is very bad. Very bad. You don't in any case want your algorithm blowing up exponentially, especially if it's based on the size of an integer. So, yeah. Anyway. Yeah, so I guess that's our time. We'll leave it there. I will answer any questions that might be lingering in the chat. But yeah. Let me see if there are questions that have not appeared, because that's been a while ago now. Nope. Okay. All right. Coolio. So, yeah. Any questions? Cat. Okay. There we go. Say hello to the people, Mars. Oh, that's the microphone, yep. 2 cats at the same time. I don't know, I only have 2 arms. That's a bit much. Yeah. Yeah, this is boring for you, isn't it, Mars? He's like, I was asleep. I was asleep and you woke me up. I expect treats when I'm woken up from sleep. Or at least the ability to lick your nose. How about this? You want to smell this? Smell this? Is that good sniffs? Oh, he's purring a little bit now. Cool. All right. Yeah. There we go. Is he named Mars because his fur has a reddish tint? No, actually, his name is Martin properly, which it was, I don't know, it's kind of a long story, but sort of in my household, we got Mars like in the spring after the fall in which my wife and I moved in together, and in my household, prior to establishing my new household, the custom is to give the custom is to give cats names which once belonged to ancestors or dead relatives. And one of Allie's on her side was Martin, and he seemed like a Martin, so we named him Martin. But of course, if you look at the root term, like the root etymologically of Martin, it's actually like Martin, Marshall, Mars. So it's like derivative from the term Mars anyways. So we just call him Mars. You know how like cat names get abbreviated, right? Like the other one whose name is Marimba. We usually call her Rimby, just because she's it's nice. It has a certain percussion to it. But yeah. Anyway, yeah. Good. Cool. Well, if that's everything, I'll let you guys get back to your lives. Yep. Cool. Beware the Ides of March. That's all I have to say for you on this, the first day of March. Take her easy, folks.